Before we get into this problem, I want to give you a concrete example of what we mean by a self-invertible integer modulo something. 4 squared, the same as 4 times 4, right? So 4 squared is congruent to 1. I'm just using a small modulus, mod 5. All right, folks, 4 times 4 is 16, and 16 minus 1 is a multiple of 5. And of course, 1 squared is always going to work in any modulus. Congruent to 1 mod 5. And it turns out for prime moduli, it's always going to be p minus 1 or 1, okay? Now, we'll prove that a little more thoroughly down here, but we're supposed to look, we're given a polynomial, a cubic polynomial, and we're looking for a positive integer, a, such that f evaluated a is self-invertible by the same sense, or the same sense of the definition. Now notice that this statement right here actually implies that p is a divisor of I squared minus 1. Or this is literally an equivalent way, and let me envelop that in parentheses. Okay? But notice this is equivalent to p divides either I plus 1, just using the difference of two squares result, or p divides I minus 1. Okay? So that helps us along in the rest of the problem here. In other words, you can see right here, if you think, let's see here, well, in other words, I plus 1 or I minus 1 are the only possibilities. That's just a property of prime numbers, okay? So let's move along. Now, we're trying to find an a such that f of a is self-invertible, and so literally we're doing this definition here. Okay, we're actually literally doing this definition on this line right here, except it's for the image of the function. Okay, now f at a, it's all right in front of you. Now, based on this right here, and also the fact that you can see right here, you either get 1 or p minus 1. Okay, and again, I didn't prove this rigorously at all, but it's either 1 or p minus 1. In this case, p was 5. And it's like that for all other primes, and that's really behind the proof of Wilson's theorem, part of the proof at least. Okay, the very same idea is being used right down here. We have it's congruent to 1. This is just the definition of self-inverting, and so this statement is true for the same reasons as this statement right here, and also just this special case right here should convince you it's true. Okay, I didn't prove it rigorously, but anyway, hopefully it's convincing enough to go with it. So we can remove the squaring symbol. Just in other words, we're taking the square roots in a modular arithmetic setting. Okay, now the easiest one to work with as far as finding a solution is this bottom one, -1, because you can see they'll cancel out on both sides of the congruence. The -1s are on both sides of the congruence here. So we get to this statement just by considering the negative version, okay? The positive version will give you a constant of 2, and it's a little bit more work since it's a cubic with a constant term. Here we can actually use some factoring here to get a result pretty quickly. We can factor out an a, okay? And we get this result right here, a squared plus a plus 3. Is congruent to 0. You see this theme of p dividing a quantity. This would mean that either a is equal to 59. But notice that if a is equal to 59, that makes it congruent to 0. And we're not interested in a 0 solution. Okay? Or it would mean that 59, and this is the one that's going to lead to a solution, 59 would divide a squared plus a plus 3. Now, 59 being a multiple of itself implies, and this is just checking, implies that a is equal to 7. Okay. Now notice this is an incomplete problem in the sense I only considered this bottom case. Okay. I only considered the bottom case. There may be solutions associated with the cubic where you would have a 2 here, a plus 2 right here. Okay. You have a plus 2. But here we get a equals 7 just by checking. Now, if this had been a larger degree thing, you know, we just got lucky that at 59, it works out nicely. It could have been another multiple of 59, like it could have been 118. I haven't checked for 118, you know. But so a equals 7 is a solution. And of course, you can add multiples. The more general solution, of course, would be a is equal to 7 plus any multiple of 59. And that's simply because 59, it's kind of weird to see this, but if you want to do 59k here, this is just 0 from a modular arithmetic perspective. And also you can see that if you actually just substituted this in, every term, you know, would have multiples of 59 in it. You know, a lot of the terms would have multiples of 59 in it, which is just 0, you know, mod 59. So it's very easy without thinking about modular arithmetic to note that this is a general solution based on this particular solution. Okay. And again, I haven't even checked. I'm not even sure what luck you would have for the other case. That's why I kept the instructions kind of chicken shit here. Just find a solution. There may be more, but I know that a equals 7 is one solution. So we'll write a equals 7 is what we're looking for. And again, you can explore more into this problem, find out. There may be another class of solutions associated with the other one. I'm not sure. But anyway, a equals 7 was at least what I was looking for this problem. Okay.